Hello, everyone. I'm excited to present our work, Arbitrary-Resolution and Arbitrary-Scale Fast Super-Resolutions with Implicit Representation Networks. Let's begin with the introduction. What is fast super-resolution? Fast super-resolution involves generating high-resolution factual image from their low-resolution counterparts. Some previous works enhance details by leveraging facts priors or employing attention mechanisms. Fast super-resolution offers advantage in downstream factual-related applications. However, existing methods face challenges. They are highly sensitive to variation in input resolution, and their applicability is limited to a specific upsampling scale. Our goal is to address this limitation by developing a flexible FSR method, which is capable of handling a wider range of upsampling scales and input size. And we call our methods Arbitrary-Resolution and Arbitrary-Scale Fast Super-Resolution. We leverage the concept of implicit lunar representations, which represent objects as MLPs, mapping coordinates to signal values. In 2D, we term it implicit image functions. The continuity of coordinates allows us to achieve super-resolutions at any upsampling scale. Now, let's move on to related works. Previous FSR methods incorporate factual priors or leverage attention mechanisms. However, they have two limitations. The first is applicability to a specific upsampling scale and sensitivity to variation in input resolution. Previous INR-based SISR methods propose a local implicit image function to learn continuous image representation. Using local relative coordinate and lantern codes as input to predict RGB values. However, they lack a global view, and some of them ignore the spectral bias problems. Also, similar to FSR methods, they lead to artifacts when the input size changes and exhibits poor robustness when upsampling scale changes. Now let's discuss the challenges. We compare our proposed ARASFSR methods with SISR methods, FSR methods, INR-based SISR methods. The figure highlights difference in patch-based training in SISR versus the needs for the whole low-resolution fast image as input in FSR, resulting in a global approach. Conventional FSR methods have limited practical application due to fixed upsampling scales and sensitivity to input resolution variations. Applying INR-based SISR methods to fast image is challenges due to the lack of a global view. To address these issues, we propose ARASFSR, utilizing the implicit representation networks for factual image of any resolution and adaptable to changes in input resolution. To overcome challenges for FSR and INR-based SISR methods, this paper introduced ARASFSR, featuring three novel designs. First, ARASFSR employs implicit image function for super-resolution at any upsampling scales. Second, a local frequency estimation module reduces spectral bias, capturing high-frequency facial texture information. Lastly, a global coordinate modulation module guides FSR, leverage prior factual structure knowledge for effective resolution updation. Next, let's move on to proposed method. In our method, we employ implicit image functions and propose a local frequency estimation module and a global coordinate modulation module. For a continuous image, the RGB value S at the target coordinate xs is defined by the following formula. We perform feature unfolding by concatenating feature from a 3x3 neighborhood around each pixel of the feature map to enrich it. Next, we incorporate an additional scaling ratio as conditional input to reduce spectral bias and adapt to any upsampling scale. Next, we perform local ensemble to address the issues of discontinuous prediction. The local frequency estimation module reduces spectral bias using an encoder-decoder architecture to model the conditional distribution. And the global coordinate modulation module incorporates prior factual structure information into FSR by mapping the global coordinate into a high-dimensional space using positional encoding. Lastly, the skip connection helps effectively learn high-frequency components in residual networks, also improving convergence stability. So far, this covers the entire architecture. Now let's move on to experimental results. We conduct experiments on 4 datasets: Celeb AHQ, Celeb AHQ NNJPEG, SC phase, Helen. First, we compare the performance of our approach with INR-based SISR methods at different upsampling scale and on the Celeb AHQ dataset. The table presents a quantitative comparison with ARASFSR, achieving comparable performance for in-distribution scales, and outperforming other methods for out-of-distribution scales. The figure visually demonstrates that as the upsampling scale increases, INR-based SISR methods produce SR results with blocking artifact, while ARASFSR generates stable results with possible details. Second, we create the Celeb AHQ NNJPEG dataset by downsampling Celeb AHQ using the nearest neighbor method and introducing JPEG compression artifacts. In this figure, we observe that previous work encounters artifact when the input resolution of facial image changes, as the implicit image function is constrained to a local view. The red arrows indicate misplaced landmark and artifact, and our results display clear factual landmarks. The SC phase dataset, containing facial image captured by surveillance camera, demonstrates our method's applicability in real-world scenarios. We also conduct experiments exploring various input resolution and upsampling scales in supplementary materials. Lastly, we compare our approach with FSR's methods on Celeb AHQ and Helen dataset. The quantitative results indicate that our methods produce comparable performance to our FSR methods in both match and mismatch scenarios. The visual comparison illustrates that our method produces high-quality results with minimal artifact and clear factual feature. In conclusion, we propose an arbitrary-resolution and arbitrary-scale fast super-resolution methods. Our framework employs an implicit image function that handles changes in upsampling scale. Furthermore, our approach incorporates a local frequency estimation module to capture high-frequency information for factual texture, and a global coordinate modulation module to guide factual structure, ensuring effective operation across various input sites. Through our experiments, we demonstrate the robustness of our proposed method compared to state-of-the-art methods. Thank you.